Hello everyone, I'm Fatima Hanani and I'm a doctoral student at the Lastimi Laboratory at Mohammedia Engineering School. And today I will present you my paper entitled Fuzzy Logic Framework for the Assessment of a Local Accessibility Based on Built Environment Characteristics, written by myself and Soulhi Aziz. In this regard, after introducing my work and explaining the problematic, I will expose the research context and method, followed by the result that I have obtained. And finally, I will end my presentation with the contribution of my work and the conclusion. First, in both scientific and professional community, we need the need to integrate transport and land use policies in order to achieve more sustainable urban development is widely recognized. Accessibility can provide a conceptual focus for this integration because it is related to both features of the transport system as well as the land use system. Besides, accessibility has recently gained ground in city institutions that can use it most effectively as a planning tool and also as a tool for evaluating the effectiveness of policies for land use and transport systems. Despite a substantial amount of research on built environment and transportation, there have been limited studies on the importance of built environment characteristics in terms of accessibility. Moreover, in order to identify effective strategies for increasing sustainable and active mode of transportation in urban areas, planners need to identify how land use planning in neighborhoods affect accessibility. Hence, this paper employs a new approach for measuring accessibility against land use features. To begin with, according to the accessibility literature, there are three methods of measuring accessibility that are cumulative opportunities, gravity-based measures, and utility-based measures. These accessibility measurement methods present several issues and limitations, namely the lack of understanding of accessibility concept, especially among politicians, technical and computational complexity, lack of standardized software availability and the data, and precision that concern variable and intervals for the first method. Therefore, all methods presented above calculate accessibility as a function of transport system parameters like cost, travel time, and distance. That's why the aim of this work is to highlight the fact that accessibility is also an outcome of urban design. Thus, we present a new method based on fuzzy logic to assess the accessibility according to the urban characteristic of the area. This method, we call it built environment-based accessibility measure. One may wonder why the use of fuzzy logic. In fact, it is difficult to set up measures of accessibility with the precise variables and intervals. Besides, city managers need to read, understand, and easily modify the rules of the accessibility calculation model. Moreover, with the fuzzy logic, the accessibility measures is easy to understand and interpret thanks to the use of linguistic variables and the human reasoning. To measure the impact of the land use in travel behavior, five urban characteristics are studied called 5D variables, standing for density, diversity, design, destination accessibility, and the distance to transport. For our study, we chose to limit our research to three first variables considered by scientific literature to be the key factors that most influence active transportation modes. After presenting the variables, we now focus on fuzzy logic methods. This approach attempts to stimulate human reasoning and allows integration of imperfect data in a decision process. The basic characteristics of fuzzy logic are linguistic variables, universe of discourse, function of membership, and the fuzzy subset. Moreover, the operating principle of fuzzy logic system includes three phases: fuzzification, fuzzy inference engine, and defuzzification. To model our system to evaluate local accessibility, we have defined three input variables and one output. As shown in this table, for each variable, there is the formula, the fuzzy subset, and the membership function. These variables are activity density index EDI, land use mix LUM, street design and connectivity PRD, local accessibility index LIE. The second step is a fuzzy inference. This step is where human reasoning will be applied. This phase consists of two steps. The first one is to build decision rules and to find for each of them the membership rule of the conclusion. The second one consists of the aggregation of conclusion. For this step, we use the Mamdani inference mechanism. As you can see, here is an example of rules for our fuzzy inference system. Finally, we can evaluate the local accessibility through our fuzzy system. It is the defuzzification step. To study the relationship between our input variables and the local accessibility, we will proceed to the analysis of the surface graphs of three cases. Case 1. In this case, we set the density to the average value, and we see how our system reacts. We can see in the graph that when the density is medium, we can only expect the medium value of accessibility. Therefore, when the BRD is low, accessibility remains low, whatever the value of LUM variable. This supports the fact that the ease of access is an important component to consider when studying and planning local accessibility. Case 2, as we can see in this figure, when we set the LUM to medium value, we notice that this case presents the same result as the previous one. We can conclude from case 1 and case 2 that the land-use mix has the same impact on a local accessibility as the density of activity. In case 3, as we can see, in contrast to the two previous cases, the most important remark is that accessibility can reach high values, but with one important condition. Both EDI and LUM must be high. In addition, this graph shows two main findings. Local accessibility can be medium when at least one of the two has a medium value. Local accessibility is low when at least one of the two has a low value. This result is consistent because when the density is low, there is no reason to talk about the land-use mix. Moreover, when the density is high and the land-use mix is low, we conclude that the area presents only one activity. In both cases, the accessibility remains low, except when PRD becomes high. In this case, accessibility becomes medium. Furthermore, we can also conclude that combination of EDI and LUM characteristics are more important and relevant to achieve a high local accessibility. As contribution of our work, we can say that our method allows us to extend the scope of cumulative opportunity method by considering the surrounding land use environment. Also, it allowed to evaluate local accessibility using the principle of the gravity method, incorporating an impedance function, capturing the access a condition to each opportunity by using the variable PRD. In addition, our model considers the two main components of accessibility concurrently, which are the ease to walk or cycle to reach destination, and the quantity and spatial distribution of opportunities. The first component is represented in our model by the characteristic street design and connectivity, PRD, and the second is represented by the combination of the two other urban characteristics, activity density, and the land use mix index. On top of that, our model presents a high level of disaggregation to capture small-scale design features at a stricter level and to evaluate non-motorized trips. Our method can also help city decision makers predict the impact of land use management strategies on improving local accessibility, such as densification of activities, mixing activities, and bringing them closer together by improving walking and cycling conditions and pedestrian-friendly environments. Nevertheless, our method presents some limitations. Obviously, for a model to be relevant and effective, it must be exhaustive and consider all the factors and elements that can influence accessibility. Even though our model tried to consider the two main components of accessibility, we could not consider how these two components are perceived and used by individuals with different characteristics. Therefore, our model has only dealt with one part of accessibility in the city, which is the local accessibility that concerns only the active mode of transport. And it did not consider the regional accessibility and the other modes of transport. To conclude, it is widely known that accessibility is a major effect of transport system. However, this paper shows that accessibility is also a matter of urban planning. In particular, we have found that local accessibility can be defined by three urban characteristics: activity density, land use mix, and street design. In the perspective, and to conclude this work, our model can be extended to treat the question of accessibility in a global way and to consider the regional dimension. Also, our work can be improved by testing it with real data to better calibrate it. Thank you for your attention.